Okay, today we are going to start to talk about neural network. So it's very important that we start with the basics. Then gradually we can and we're going to talk about how to implement that. In neural network, for this courses, we're going to focus on two architectures. So there's something architectures. One is MLP, one is CNN. Okay, so and today we're going to talk about a very basic idea about MLP and CNN. There are two more and architectures that I'm not going to cover today, as I'm not going to cover in this courses. The other two are not covered is RNN, convolutional neural network, transformers. So basically these four and architectures using them, I would say most of the current architectures that we already have. Okay, so before we get to the neural network, let's revisit multi-class and the classification problems. So because and review multi-class classification. Okay, so first thing is, I mean, this is usually that and we did that through the logistic regressions. As I think we spent a significant amount of time on the logistic regressions. So we talk about and how to use in packages to implement that and to work on this multi-class and the classification problem. To be more specific, the idea is we give the training data set. So basically the training data set looks like this. So I have a feature of xi, and I have the target, which is yi, I from 1 to the n, and then the input feature. X of I in R big D. So these are the features and the target or the label. This yi is in from 1 to the k. Okay, for k class classification problems. So the goal, so this is given. The goal is I want to learn a function, right? So such that learn a vector value functions. With some model, with some like tunable, like model parameter feeder, so like theta. So basically f x theta is R big D to the 0, 1 to the k. All right, so I'm trying to learn this vector value function. So you can think about right here for this one is actually the probability mass function. So that means it's the probability. So you can interpret this and this right here. So you say that like ceased entry. So this is actually give you a vector, right? So the FC, which is the ceased entry of this, is actually can be interpreted as the predicted probabilities. Okay, that this input data X I belongs to C, belongs to the class C. And for each C from 1 to K. Right, so this is basically actually trying to give the predicted probabilities. So the main idea is we want to find the optimal theta, and hopefully, and we can get, and hopefully, and we can like tune the theta such that for all those training examples, so this is my training examples, my argmax of C, which is all my predicted probability, I find out the corresponding C to maximize the predicted probability is precisely the label that we are looking for. Okay, so this is the whole idea, is to tune these thetas. And hopefully using some optimization algorithm, and such that we can find the maximum so the maximum and the labels to make these predicted probabilities to be the maximum, which is exactly the yi. So so this is actually the general framework, and this general framework will be the same if we want to work on even and work on the neural network. So this is a very good scenarios to work on the neural network, because think about neural network as being task is still being the multi-class classification problems. But so previously we're using logistic regression, right? So logistic regression is being very, very popular here. So the logistic regression here, this F right here is actually just composition of the linear function and the softmax functions. So basically F right here is a linear function then composite of the softmax. So what does it actually means? So to be more specific, I'm going to map this input features into linear functions. Like this. So you can, so this Z has a name, is called pre-activation vectors. W is actually the weight matrix. B is actually the bias vectors. So you can think about this is nothing but just a linear and a regression problem. So this is the linear models that we have already. Okay, so then after linear and the linear functions, then we apply the softmax functions to make sure this is actually give you the probabilities. So this is the first step. The second step is, so this is linear. The second step is softmax. So, and this actual output is my softmax of my z of x. Right, so so this actually output the predicted probability for k classes. So this is, to be more specific, this is softmax. So you think about W is a matrix, right? So W is in K by D, and your X is actually RD, and your B, the bias, is actually RD. No, I think B is actually RK. Okay, so this is softmax. So you do it for each and each of this. I'm going to do it row by row. So this is W1 X plus B1. And I have WK X plus BK. So you think about this, my W is actually composed of W1, W2, until we have WK. Okay. So what is this softmax of this vector? This is actually give you something like that. So I think I already mentioned these kind of things before, but it's basically it's you take exponential of each entry. So entry wise, and then you normalize it such that to be a probability. So this is W1 X plus B1 divided by summation of J from 1 to dk exponential of Wj X plus Bj. So you do the same thing for the rest until to the end exponential Wk X plus Bk, then divide by the same. Okay. So you can show this each entry here is between 0 and 1, and the sum of this is actually equal to 1. Right? So this is pretty obvious. So this actually gives you the probabilities. And also the theta right here, I mean, I want to get some tunable parameter theta. So basically this theta right here is actually all these weight and also the bias. So theta is W and B. Okay, so With that, we can, so we need to, so we can change the goal a little bit to make things a little bit more concrete. That my goal is actually to find a parameter theta such that it actually minimizes the training loss functions. Minimize the training loss. So what is the training and then the loss functions that we can use? There are two commonly used loss functions in the logistic regressions. But the most important part is actually to use the cross entropy loss. So this loss is usually used is called cross entropy. So the definition of the cross entropy is given as follows. So say this is the loss of f of x of I, theta, and the y of I. This is minus, so the cross entropy loss is minus of the logarithm of f yi x of I. So we know this is actually give you a vector. What you only get is only choose the entry that its entry is corresponding to yi's entries. So we know this is strictly non-negative, bigger or equal than 0, because my probability is always between 0 and 1. All right, so why this is given like that? But by definition, this cross entropy is actually defined like this: minus j of yj I log of fj xi theta. So this is actually one hot encoding of yi. So this is, I'm going to call this yj is the one hot encoding. The one hot vector. Yi. So basically, it's only the yi entry is equal to 1, everything else is just being 0. So this is being the definition actually of the cross entropy loss. But since only entry that it's actually contributing is happen to be j equal to or like and yi, right? So this is basically, so that's why this is actually equal to a minus of logarithm of f yi x of I. So this is actually the simplified version of the loss. So so the point is, if this is actually the loss, so that means for each of the data entries of xi and yi, I want this whole thing, which is my predict probabilities for class of yi, to be as large as possible. So the goal here is basically to make this is f yi x of I theta, which is the predicted probability for class of yi as large as possible. Right, so this is actually the predicted probabilities for class of yi. All right, so, and of course this is for one single data, and the total loss is we need to sum all the cross entropy loss on the full training set. So the training loss is actually the cross entropy on the full training. So here, I showed the cross entropy on single data set, a training data set. But of course, we need to sum them together and take the average. So this is the loss is actually a function of theta. The loss is always the function of theta. Is we sum all this cross entropy loss for each entry, then divide by n. So this is minus 1 over n of log summation of I from 1 to the n logarithm of f yi x of I theta. Right, so this is basically the average of the cross entropy loss. And of course, this is the training loss, but in practice, in the logistic regression for the multi-class and a classification problem, we're usually adding a penalty here. Right, so because like this whole thing is, my overfit, so usually we're going to add L2 penalty. It's like ridge regression. Usually we adding the penalty on the W because this is like the most likely to have a problem to add a penalty to reduce the overfittings. So this happens in the logistic regression. So this whole thing is actually the logistic regressions. So to give you some idea is we can think about all these features being something like, and look like a neuron here. So if we have D dimension features, so I have a D neurons here, right? So each actually feeding certain values. So this is R big D. So what I'm going to do here is basically apply a linear layer. So this linear layer is basically a softmax. You can think about it. This is the softmax. So this is actually the output. So this is RK, which is K labels. And everything is actually fully connected and so on, right? So this is all fully connected. So this is a fully connected layer. So that means they're all linear, fully connected. After that, I'm going to apply the softmax. To turn these values into actually predict the probabilities. So this is my output. Right, so a very simple ways of thinking of the neural network is actually the logistic regressions. So I mean, you can think about this as being an input layer, and you apply a linear and transformation, then you apply the softmax. You get RK, the value being the probability, so this will becomes the output layer. There's like, and there's nothing like in the middle, just being a input and output. So you can think about and the logistic regression as being like being like the simplest possible neural networks that you can think about. So this is just give us a like foundations, and to give the further and further ideas for the neural network. So basically, the neural network, which is I mean, the first things that we want to do is MLP. So like MLP is called a multi-layer perceptrons. So let's talk about the MLP. I mean, slightly more complicated than the logistic regressions. Okay, so what this is doing is I still have these input layers. So this is say R5. So I have a 5 neurons. So this is X1, X2, X3, X4, X5. So basically I have 5 dimensions. Then, I mean, this is my input. And I'm going to add something called hidden layers. And I still have the output layers. Okay, so I say, I mean, this hidden layer is additional to the logistic regressions. Say you have 4 hidden layers neurons. Z1, Z2, Z3, Z4. Okay, so they're all fully connected. So that means I have weight passing to the Z1. I have weight passing to Z2, Z3, Z4, and so on. Right, so they're all fully connected. Okay, it's a huge mess. So this is basically all these value, and you're going to take a linear transformation. I'm going to show you what is that momentarily to combine this and information and passing into the hidden values. Sorry, the hidden neurons. So these are actually neurons. This little circle is actually the neurons. So then you are going to do the similar things from hidden into the output. So here I'm going to have 3 and 3 labels. So basically my K is equal to 3. It's like 3 label classification problem. Then this is fully connected. And each layer, and each neuron in the hidden layer will be connected to the output neurons. Okay, so the output neuron will output the probabilities for this data of say X. Right here is my data, is my features. My features looks like this: X1, X2, X3, X4, X5. So this is one single data. Okay, so say this actually give you the probability of 0.1, 0.6, and of 0.3. So this all three probability actually sum to be 1. So this actually predict of the labels corresponding to this ones, which if we just label into class of 1, class of 2, and a class of 3, then it actually predict this X features and X data entries to be predict to be class of 2. All right. I hope this is clear. Okay, so this is, and to be more specific, so this is input layer, and right here, and this X1 to MX5. From the input features, here we only have 5 dimensions. So, and basically my input features have 5 values. So the middle one is the hidden neural layers. So basically processed input from the previous layers, and output the results to the next layers. Here we have 4 hidden neurons. So right here, I'm going to apply the so linear transformation. Then I'm going to apply something called activation functions. So this is, I'm going to call this right here. This process is A of X is equal to G of W1 of X plus B of 1. Okay, so this is actually as dimension of H, which in this case is dimension of 4, right? Because I have a 4 hidden neurons. Okay, so my W1 here is actually the and a 4 by 5, right? Because this is, you can think about this is R big D. So this is my input feature. So this is R big K, which is the number of labels and labels. So in the middle, I'm going to call it RH, which is the number of hidden neurons. H is the number of hidden neurons. So in this case, is my D is equal to 5, H equal to 4, K equal to 3, right? So this W1 is actually has a dimension of H by big D. And B1 is actually R4. So so this is actually the weight matrix and the bias factor for this dense linear layers. So this is the dense weight and bias for dense linear layers. So the reason I call it dense because I assume my W1, which is my weight matrix, has, it's always non-zeros. Okay, so that means it always have some contributions to it, whether it's positive or negative. Then the G here, I'm going to define this as R to R function. So this is actually defined entry-wise. So that means, although this output of W times X plus B is actually a vector, but I'm going to apply this G functions entry-wise. So that means this AJ, which is equal to G ZJ. So this is element-wise operations. So this is very common in neural network, right? So, so this is called, and G is called nonlinear activation functions. Okay, so there are multiple choices for this activation functions. I mean, this is so like pretty much very popular. So I'm just like and give you some idea. So and for example, you can choose the choice of G varies. So for example, you can take very popular one is called ReLU function of X is equal to maximum of 0 and X. Just, I mean, it's like, and it's smaller than 0, this ending, and it's ended with 0. If it is bigger than 0, it's X. The number 2, so you can do sigmoid function, which is 1 over 1 plus exponential minus X. Okay, or you can do hyperbolic tangent, exponential of 2x minus 1 divided by exponential 2x plus 1. So this is hyperbolic tangent. So and basically they are, and you can choose like any of this. There are many other more activation functions that you can choose. You can choose leaky ReLU. You can choose a lot of interesting activation functions. So there's no unique way and to do so. Just a second. Okay, so this is the first layer. And then, so we talk about from the input to the hidden. Then we can talk about from hidden to output, right? So this is not yet finished. So, so from hidden to output, is basically we're going to take information from the hidden neurons and to get the output neurons. So this becomes softmax of W2. I'm going to, this will be another weight matrix, but this I'm going to apply to the AX. AX is right here. It's defined right here. So I mean, this is the value of the hidden neurons plus B2. So if we actually plug in the formulations for AX, so this is becomes softmax W2 G W1 X plus B of 1 plus B of 2. So this is, we know this is between 0, 1 to the K. In these cases, this is W2 and B2. is also the matrix weight and biases for this second layers from hidden layer to the output layers. So in this case, it's my W2 here is in K by H, and my B of 2 here is in RK. So basically, in this cases, my model parameter theta is W1, W2, B1, and B2. Okay, so these are actually the model parameters. But think about how many parameters that we have. So this W1 here, this will be 4 by 5. W2 here is 3 by 4. This B1 has 4, B2 has 3. Right, so this is number of parameter need to be estimated. And also, in order to tune this parameter, we actually have to define the loss functions. So here, again, we're using the cross entropy loss. So the loss minus 1 over n summation I from 1 to the n log of f yi x of I theta. Right, so this is exactly the same thing that we have used in the logistic regressions. So you can think about this multi-layer perceptrons is actually compositions of functions. So you have linear layer, then you apply nonlinear activations, then you apply the linear layer, then you apply the nonlinear functions, nonlinear activation functions. So you can think about each neuron is actually a functions. It will accept input from the previous layer and output for the next layers. So the way you think about it is if the neuron is activated, it has high value, it will be muted that it has low values. Okay, so so one of the advantage that we use for the Softmax output layers is it actually interpret as a probability. But one of the issue for the Softmax functions is this last layer right here is not element-wise. One of the reasons that this is not element-wise is because it actually, you need to normalize it right here with the weight. So this is actually the weight. So that's why sometimes what we do is we are not using the Softmax in the last layers. So we can change the last layer to use the sigmoid functions. In the output layers. And also, correspondingly, you are not using the cross entropy loss. Instead, you're going to be using like logistic loss. So this is sigmoid functions and the logistic loss. So what does that mean right here? We're using softmax. Instead, I'm using sigmoid. Sigmoid here, we don't actually need to normalize it with a summation of the exponential function. So that means it can be applied entry-wise. So then the loss is actually given as follows. So this is the logistic loss. Well, minus 1 over n, summation I from 1 to the n of log of f yi x of I theta plus, so this is the logistic loss. So this is being used in the binary. So sorry, I'm in the logistic regression as well. So this is sum of j is not equal to y of I. So this is and also very commonly used in the logistic regressions. Log of 1 minus of fj of x of I theta. Okay. And the same thing here. This so we can use the idea of the one-hot encoding with the one-hot vector. That yi as a vector is the standard vector of yi. Then this actually can be written in even more compact form. That is minus 1 over n double summation, right, from 1 to the n, summation the j from 1 to the k of the y j of I log of fj x of I theta plus 1 minus yj of I log 1 minus fj x of I theta. Okay, so this is basically I used one-hot encodings. So this is one-hot encodings to simplify the summations. Here we're using, I mean the logistic loss instead, and rather than cross entropy. Okay, it actually depends on so whether we're using the sigmoid or not. I mean, so if we're using softmax, we know this is actually a probability and the vectors we can use in cross entropy because we know this and the probability is sum to be 1. For the sigmoid, they are just some positive values. So we are not, so we don't know. So I mean, and that is and the summation is not equal to 1. This is not probability, so that we can only using this kind of logistic loss instead. In fact, you can also using like and the square loss if possible. You can even using square loss. And but there's some reason that you probably shouldn't use the square loss, but yes, you can to use. One of the reason that the square loss is if you're using square loss, and you are likely to have some like gradient vanishing property. So this is something that only when you're tuning that you will find out something is like that. But usually, yes, hypothetically it's doable, but in practice you will find out this square loss things is very hard to tune just because square loss usually will give you the vanishing gradient. So basically you can do square loss, so this is still the one-hot encoding of value. All right, so square loss. All right, so basically the whole idea, and the whole idea is we're trying to using this loss functions to find out the best possible parameters of the theta here. So basically in this case is we want to find out W1, W2, B1, B2. So this is the weight and the biases. And they are all, and this is dense fully connected layers, which basic says, and W1, W2, B1, B2, they have like, and essentially we just assume they are non-zeros and it could be positive or negatives. And that's why it's fully connected. It means this value is non-zero, so it's fully connected layers. Right, so and also it's a dense. Dense means there's no like, and essentially there's no zeros. So why? So the question is why this actually work, right? So I mean, so the reason that actually this whole thing actually will work is because there is a theorem. Okay, so basically the reason that this is and like an MLP multi-layer perception will work is we have the following theorem. That means, I mean, by the end of the day, we're trying to learn an underlying decision function f hat that can map any data to its correct labels. So the idea of like deep neural network, it can approximate that kind of decision functions with arbitrary positions given sufficient depth of the neural network. So this is guaranteed by the universal approximation theorem, which basically for arbitrary like Lebesgue measurable functions, and the Lebesgue integrable functions, you can give a position of epsilon arbitrary and epsilons. So there will exist a fully connected deep dense ReLU network with certain idea that this D and the width of this things is D plus and less equal than D plus 4, such that we have such kind of like neural network you can think about as output functions. And to satisfy these error is sufficiently small in some senses. Okay, but of course, to learning such kind of optimal deep neural network could be very, very difficult. In general, they might not be even possible because of this highly non-convex optimizations. Right? But theoretically, with that being said, the deep neural network can basically do almost everything that you want, can approximate almost every functions that you are interested in. Okay, to recap what we already done here. So basically, this kind of neural network is called deep neural network. And sometimes, as I said, it's called multi-layer perceptron, MLP. So this is the first architectures in the neural network that we have been talking about. If this has more than 2 layers, like more than 2 hidden layers, that's called deep neural network. Otherwise, if we only have a 1 hidden layer, like we just showed, that will be shallow neural network. All right, so, and you can see right here, so this is a very commonly questions of to and distinguish the cats and dogs. So my feature is actually the images of cats and image of dogs. I have a bunch of the image of cats, image of dogs. So that means this is my input layers is actually the number of pixels of the images, right? And also my output is just being cats and dogs. So this is 0 or 1. So this I only have a binary classification problems. Right here I'm using, right here you can think about I'm using 3 layers of hidden layer, and each layer has 6 neurons. So this is actually called a deep neural network, right? So the deep because we are having 3 layers, such that I'm using this 3 layers neural network trying to approximate, trying to capture, and trying to and perform this binary classification problems. But of course, one of the issue is we are doing some image processing. Image processing turns out usually have a very large number of pixels. For example, if you're take pictures of your own phone, probably they have millions of pixels. Then your input layers will have millions of the neurons, right? So that means there are way too many informations that you need to process. So if you only put like 10 or 20 neurons in the hidden layers, it might not be enough to process the data. So that means this neuron will reach certain capacities that cannot process the data very well, right? So, I mean, in order to process this very well, you probably need to also have thousands or tens of thousands of the neurons in each layers, in layer 1, in layer 2, in layer 3. As a consequence, if we have that kind of situation, then we will have using the MLP to process that we have way too many neurons, right? Because think about my input layers have a 1 million pixels. Then my first hidden layers, I say I have like 10,000 neurons. That's 1 million times 10,000 weight. that we need to learn, right? So this is really a lot of very large matrix need to be learned from the data. So it's, I mean, if that's the case, is usually we have a big problem, because sometimes we don't even have that side and then that's such big memories to store that kind of matrices. So this won't be a very ideal. So that's why in terms of images, it is not a good idea to using MLP layer perceptrons to process the images to do these kind of binary classification problems. Just because this image actually has way too many pixels. And also these like nearby pixels are highly correlated. So if we just treat each pixel are kind of like independent and feed them into MLP, it usually won't be a very good idea. So that's why it's very important to introduce the next, and the next important thing is called convolutional neural network, which can process these kind of images data extremely well. So this will be taught in the next lectures. All right, so that's all I want to talk about today.